Welcome to this lecture on the sampling distribution of a statistic. Imagine you are cooking a massive pot of soup for a huge party and you want to know if it has enough salt. You cannot drink the entire pot to find out, so you take a small spoonful to taste. That spoonful is your sample. Today, we will explore the mathematical foundation of how we use small samples to make highly accurate predictions about massive populations. Building on our soup analogy, let us understand what a sampling distribution actually is. If you took another spoonful from a different part of the pot, it might taste slightly more or less salty. If you kept taking thousands of spoonfuls and wrote down the saltiness of each one, you would see a pattern emerge. Most spoonfuls would be very close to the true average saltiness of the whole pot, while a few might be unusually bland or overly salty. This overall pattern or shape of all those possible spoonful results is exactly what we call a sampling distribution. It tells us how much our sample results will bounce around just by pure random chance. Now that we have an intuitive feel, let us define this formally in statistics. We rarely have access to the entire population, so we draw a random sample of size n. A statistic is simply any value calculated from this sample data, like the sample average. Because every new sample we draw will contain slightly different individuals, the calculated value of our statistic will change every time we take a new sample. This means the statistic itself is a random variable with its own probability behavior. The sampling distribution is the complete probability distribution we would get if we took every possible sample of size n and calculated the statistic for each one. To make this completely clear, let us look at this visual representation. At the top, we have our original population distribution, which is quite wide. From this population, we draw several different random samples, represented by the dotted circles in the middle. For each sample, we calculate its mean. When we plot all these sample means together at the bottom, they form a new curve. This bottom curve is the sampling distribution of the sample mean. Notice how it is centered at the exact same place as the original population, but it is much narrower, meaning the sample means are tightly clustered around the true average. Having seen the visual, let us focus on the most common statistic we calculate, the sample mean. We want to know how the sample mean behaves if the original population is already perfectly bell-shaped, which we call a normal distribution. Suppose our population has a true average and a true variance. If we draw a sample, the sample mean is calculated by adding up all the sample values and dividing by the sample size. Because adding normal variables together always creates another normal variable, the sample mean must also follow an exact normal distribution. We just need to find its center and its spread. This brings us to the mathematical center of our sampling distribution. The expected value of the sample mean is simply equal to the population mean, denoted by the Greek letter mu. Conceptually, this means that the sample mean is an unbiased estimator. It does not systematically overestimate or underestimate the truth. If you take many samples, their average will perfectly target the true population average. In this formula, E represents the expected value operator, X bar is our sample mean, and mu is the true population mean, measured in the same units as the data. If the true mean increases, the center of our sampling distribution shifts exactly by the same amount. Now that we know the expected value is equal to the population mean, let us prove why this is mathematically true. We start with a standard formula for the sample mean, which is the sum of all observations divided by the sample size n. We apply the expectation operator to this entire formula. Since the expected value of a sum is just the sum of the expected values, we can pull the constant fraction 1 over n out to the front. Every single observation comes from the same population, so they all have the same expected value, mu. Adding mu together n times gives us n times mu. Finally, dividing by n cancels out, leaving us right back at mu. This proves our sample mean is perfectly centered. With the center established, we now need to measure the spread. The variance of the sample mean is equal to the population variance, sigma squared, divided by the sample size, n. This formula is incredibly important because it shows how the spread of our guesses shrinks as we collect more data. Sigma squared represents the variance of individual items in the population, while n is the number of items in our sample. Notice that n is in the denominator. This means that as your sample size increases, the variance of the sample mean decreases. Larger samples give us much more precise guesses that are tightly packed around the true mean. Let us derive this variance formula to understand exactly why the sample size appears in the denominator. We start by applying the variance operator to our sample mean formula. A key rule in statistics is that when we pull a constant out of a variance formula, we must square it. This is why the 1 over n becomes 1 over n squared on the outside. Because our samples are drawn independently, the variance of their sum is simply the sum of their individual variances. Each observation has a variance of sigma squared, so adding them up n times gives n times sigma squared. Dividing this by n squared simplifies beautifully to sigma squared over n, proving our result. We have seen what happens when the population is normal. But what if it is not? It might be heavily skewed, flat, or completely random. This is where the most magical rule in statistics, the central limit theorem, comes to our rescue. The central limit theorem states that if your sample size is large enough, usually 30 or more, the sampling distribution of the sample mean will still form a beautiful normal bell curve. This happens regardless of what the original population looked like. The center will still be the population mean, and the variance will still be the population variance divided by n. This is why the normal distribution is so famous. Everything eventually averages out to a bell curve. Let us look at the formal mathematical statement of the central limit theorem. Conceptually, it says that as the sample size grows toward infinity, the probability distribution of the standardized sample mean perfectly matches the standard normal distribution. In this equation, x bar is the sample mean, mu is the true population mean, and the denominator is the standard error. The standard error is simply the square root of the variance we found earlier, representing the standard deviation of the sampling distribution. The symbol phi represents the cumulative distribution function of the standard normal curve. As your sample size n increases, the standard error shrinks, making the distribution taller and narrower, but its standardized shape becomes perfectly normal. Before we move on, let us see this with a concrete example about a coffee machine. We are given a machine that dispenses coffee following a normal distribution, with a true mean of 200 milliliters and a standard deviation of 15 milliliters. We take a random sample of 9 cups and we want to find the probability that the average volume of these 9 cups is greater than 210 milliliters. Because the original population is already normal, the sampling distribution of the sample mean will also be exactly normal, even with our small sample size of 9. Our first step is to note that the expected average of our 9 cups is exactly the population center, 200 milliliters. Continuing with our coffee machine example, we need to find out how much the averages of 9 cup samples will bounce around. We calculate the standard error by dividing the population standard deviation, 15, by the square root of our sample size, 9. This gives us a standard error of 5 milliliters. Notice this is much smaller than the original 15 milliliters because averages vary less than individual cups. Next, we use the Z-score formula to find out how many standard errors our target value of 210 is away from the center. Subtracting 200 and dividing by 5 gives us a Z-score of exactly 2. Now for the final step of our coffee machine problem. We want the probability of getting an average greater than 210, which is exactly the same as finding the probability of a Z-score being greater than 2. Because standard probability tables give the probability of being less than a value, we must subtract our table lookup from 1. Looking up 2.0 on a standard normal table gives 0.9772. Subtracting this from 1 leaves 0.0228. Physically, this means there is only about a 2.28% chance that a random sample of 9 cups will have an average volume greater than 210 milliliters. Let us look at a second example, this time using the central limit theorem for an elevator weight limit. An elevator has a maximum safe weight limit of 4,000 kilograms and a sign saying maximum 50 passengers. The weight of the general population is heavily skewed to the right, meaning it is not normal, with a mean of 75 kilograms and a standard deviation of 20 kilograms. If 50 random people get on, what is the probability that total weight exceeds the limit? First, we convert the total weight limit into an average weight limit per person. 4,000 divided by 50 gives a maximum average of 80 kilograms per person. Continuing with our elevator problem, we note that the population is not normal, but our sample size is 50. Since 50 is greater than 30, it is large enough to use the central limit theorem. The expected value of the sample mean is still the population mean, 75 kilograms. We calculate the standard error by dividing the population standard deviation 20 by the square root of 50. This gives us approximately 2.828. This tells us the spread of the sample means for groups of 50 people. We then calculate the Z-score for our critical average of 80 kilograms, which comes out to about 1.77 standard errors above the expected mean. We have reached the final step of our elevator calculation. We need the probability that the sample mean is greater than 80, which corresponds to a Z-score greater than 1.77. Using the standard normal table, the probability of a Z-score being less than 1.77 is 0.9616. Subtracting this from 1 gives 0.0384. Interpreting this physically, there is roughly a 3.8% chance that 50 random people will overload the elevator, even though their individual weights are not normally distributed. The central limit theorem allowed us to find this exact probability. Having solved these examples, let us zoom out and understand why this matters so much. The concept of a sampling distribution is the absolute beating heart of all modern statistics and data science. Without it, we would have no way to measure the reliability of our data. When a pharmaceutical company tests a new drug on a sample of patients, they need to know if the positive results were just a lucky batch of healthy patients or proof that the drug actually works. The sampling distribution provides the exact mathematical boundaries of what lucky looks like. It allows scientists to declare that a discovery is statistically significant using only a tiny fraction of the data. To wrap up our lecture, let us review the key takeaways. First, a sampling distribution is the theoretical pattern of all possible values a statistic could take across repeated samples. Second, sample averages are always centered on the true population average, but they have a much tighter spread that shrinks as your sample size grows. Finally, thanks to the central limit theorem, these distributions form predictable bell curves for large samples, regardless of the original population shape. You now have the theoretical foundation to make highly confident, reliable real-world predictions from limited data. Great job following along.